little further, we're going to use the graphing calculator to find some things. And I know in the past you used the table to say, okay, it's going to happen somewhere between this year and this year. But we are going to ask that you graph and find an intersection point and do some fancier stuff, okay? Yeah, that's all I'm going to. Did I hit record already? Nice. Okay, well, that was a very boring recording so far. All right, so exponential functions, we have done, in chapter 2, we did crazy business. We did power, radical, polynomial, and rational functions. That's why chapter 2 took us the last 6 weeks, I feel like. It's just very, very long, okay? Those are all algebraic functions. You get them by adding, subtracting, multiplying, or dividing constants and variables, etc. In this chapter, we'll explore exponential and logarithmic functions. This is just my favorite. I just love this. They are considered to be transcendental functions. Doesn't it sound like we're geniuses? We're studying transcendental functions. That's why I like it. Okay. Because they cannot be expressed in terms of algebraic operations. Instead, they transcend algebra. Okay, so we're doing stuff with x's in the exponent, which then leads us to solving by using logarithms. All right, so we are doing anything like this: 4 to the x, 1/3 to the x, 7 to the negative x. It's in the form a, b to the x. So the x is going to be in the exponent. Any questions? All right, so at the top of your notes sheet, it says, when you have this function, this should have been on your desk. It's the back of the first one. This time I ran the assignment sheet on the front, okay? Because actually it had a review worksheet with extra problems for you to do on the front, and I was like, yeah, they're not going to do them, so I'll just give them the assignment sheet as part of the packet and save a tree. A blue tree, no less. Very rare. All right. A, b to the x. This constant out here will stretch or flip and make things grow faster or slower or decay faster or slower. But whether or not they are growing or decaying is determined by b. If b is greater than 1, so we're doing like multiplying by 2 over and over and over again, it's going to grow, right? Obviously. If we're multiplying by 1.02, is it going to grow? By what percent? 2%. Okay. So it might not be that quickly, but it's going to grow. All right. If b is between 0 and 1, so we have 0.6% or 0.6 to the x, so we have like something like this, then it's decaying. Because it's decaying by 40%, 60% remains after every. Nope, are we lost? Yeah. 0.6 is equal to 60%. So that's what's remaining. If we started with $100, the next time there'd be $60. And the next time there'd be $36 because you're multiplying by 0.6. Okay? Better? It's decaying by 40%. All right. Let's go. So the graphs, you're going to need to know domain, y-intercept, all the things that are starred are the things you need to know. The asymptote, the x-intercept, and the range, okay? An exponential growth function, as long as a isn't negative, will look like this, okay? It'll always go through 0, 1, because no matter what we have in here, when we put whatever b is, when we put a 0 in here, does everyone understand that that's going to become 1? Okay, when we put a 0 in, whether this was 1/2 to the 0 or 7 to the 0, it's 1. So 0, 1 is going to be the y-intercept, whether it's growing or decaying. The asymptote for both of these is the x-axis, okay? They will never touch the x-axis, but they will get closer and closer. The range for both is 0 to infinity, y, bottom to top, right? 0 to infinity. The domain is all real numbers. So they're very similar. The difference is this one is going up or increasing and this one is decreasing. And what would make it look like this again, guys? 0 and 1, yes, if b is less than 1. All right, so here's an example from your notes. It just says 1/3 to the x. So if you put a 0 in there, you'd get out a 1. If you put a power of 1, 1/3 to the first power would just be 1/3. It's getting very small. But this one, do you remember your negative exponents? What does that negative exponent do? Flips it over and it makes it 3. If I put 1/3 to the -2, I'd get, flip it over and then square it. So I get 9. Okay, so by -2, it's all the way up to 9. Everybody see what's happening? It's decaying. Okay, so domain is left to right, all real numbers, bottom to top, 0 to infinity, and it does not include 0. The intercept is at 0, 1. The asymptote is the x-axis. It never actually touches. All right, the left end is going up and the right end is approaching 0. Okay, and the whole thing is decreasing. All of it, negative infinity to infinity. So let's see if we can answer. Oh my goodness. Well, throw some transformations in there, why don't we? 2 to the x would cross at 0, 1 and do what? Grow or decay? Yes, 2 to the x power. So it's y equals 2 to the x. If I put in a 1, I get out a what? 2. If I put in a 2, I get out a, what happens if I put in a -1? I get out a 1/2. So -1, 1/2. It looks like this. But what has happened with the transformations over here? Jump right in. What is on the x a -1 do? So it would look like this. What has happened to our function? Right 1 and up 1. Yes? No? Anybody awake out there? The 2 is the function itself. This is f of x. Okay? Right 1, up 1. All right, so the function would normally go through, I'm just going to do a little lightly dotted. The function f of x equals 2 to the x. You told me we go through 0, 1, 1, 2, 2, 4, and -1, 1/2. So it would look like that. But all of those points have been transformed how? Right 1 and up 1. So right 1, up 1, right 1, up 1, right 1, up 1, right 1, up 1. So the x-axis isn't the line of the asymptote anymore. What is? If we shift that line up 1, it's now, anybody know the equation of this line that's now the asymptote? Anyone? Anyone? It's a horizontal line through 1. Y equals 1 would be the equation of that line. Anyone awake? What? You don't have all this written down there, but it says it in the directions, okay? So the parent function is y equals 2 to the x. The transformations are right 1 and up 1. Okay, domain. Yes. Range. Normally, yes. But what changed with our y values? They all shifted up 1, yes. Good job. The intercept there isn't an x. And the y-intercept, how do we always get the y-intercept? Guys, how do we always find the y-intercept? Okay. So if I put in a 0 for x, I will have 2 to the negative 1 plus 1. What is that? What's 2 to the negative 1? 1/2 plus 1 is 3/2 or 1 1/2. So it should be crossing here at 1 1/2. The end behavior, oh, you guys still make me sad. The y is, how do you say on the left? X is negative infinity. And what is y doing on the left? It's getting closer and closer to 1. As we go off to the right, x approaches infinity, the y value is getting bigger and bigger. Is this whole graph increasing or decreasing? Yes, it's increasing. It is a growth function. Writing this down. Jada, you okay? This is one of the problems on your notes. Did you get some of it? Yes. What? Isn't this on your notes? Number 1? Yes. Yes, you're telling me the x values that cause the y values to increase, and the whole graph is going up, so it's x. Good question. Anybody else? All right, so here's a little slide that talks about the transformations. So 2 to the x, this would slide at what? Plus 1 on the x. Guys, you're really scaring me today. Left 1. Negative on the x. So it's this function. What is this? Reflect over y-axis. So it would actually, what would that become? 2 to the negative x is the same as, can anybody tell me? 2 to the negative x is the same as what to the positive x? Thank you. 1/2 to the positive x. Does everyone understand that? 2 to the negative 1x, well, no, would just become 1/2 to the x. So therefore, it's really a decay. Does that make sense? That if you had a growth and you flipped it across the, woo, here, it's down here. If you had a growth and you flipped it across the y-axis, it would become a decay, right? Okay. And this one, what is a negative 3 out front going to do? 2 things. Reflect, the negative will reflect it over the x-axis, and the 3 actually stretches it faster vertically, so it goes down faster. See how instead of crossing at 1, it's crossing down at negative 3. All right. So, oh, we're going to talk about E already. All right. E is a very famous irrational number. It's like pi. It never ends. The way to, it's called Euler's number. Okay. And this is the formula for how to get places of E. Luckily for us, it's stored in our calculator, just like pi. Okay. There is no formula to get pi, but this, well, I shouldn't say that. I'm sure there's something that the calculator's programmed to find pi, but 1 plus 1 over n to the n power. So if you put a 1 in, you get out a 2, but if you put in like 100, you get out 2.704. If you kept putting bigger and bigger numbers, this number approaches E. All right, on your calculator, where is E? It's just like 2.7, so it's between 2 and 3 in terms of estimating it for your graph. You can do second divide. You can also do second ln on the side over here. A lot of times we're going to use, whoa. A lot of times we're going to use this second ln because, why am I on the screen? We're going to want to put a power of E in there. and that brings up, so you don't, otherwise you can use second divide, but you have to go second divide to the power of, okay, the second ln on the left there brings up all that. All right, moving on. We talked about that. Okay, so this is like roughly 2.7 to the negative 1x. Is that a growth or decay? Yes, because it's going to be 1 over 2.7 to the x, or roughly 1/3. That's just an estimate, okay? That's really not. So this is the same as 1 over e to the x. So the parent function is y equals e to the x. The transformation is a reflection over what? Yes. All right. And I would be fine. I will tell you that in the past we have had a quiz on this stuff that was no calculator. I don't know. We've talked about doing away with that for the sake of time this year. All right. Y equals e to the x in a standard window would look like this, but we don't have e to the x. We have what? Yes, or e to the negative x, if you want to just put it in that way, it doesn't matter. So it reflects it this way. What are staying the same? Y-intercept, domain, range, asymptote, okay? All those things are staying the same. So it still goes through 0, 1. At negative 1, it would be at e, which your calculator is going to tell you is 2.7, whatever. I just wanted to put 1 point on there that was in terms of e. And then if you went over here at 1, you would have 1 comma 1 over e if you wanted to label it. But this is the idea. So the domain is, yep, all real numbers. The range, okay, Bon, you were good at range before when you weren't on your phone. Bottom to top, guys? Yep, 0 but not included. Intercepts, there's only an x. I'm sorry, there's only a y and it's at 0, 1. Asymptotes, if the x-axis is an asymptote, what is the equation for the x-axis? Y equals 0. It's horizontal. End behavior, on the left, it is doing what? Yeah, on the left, it's going up. On the right, it's getting closer and closer to 0. The entire graph is decreasing from negative infinity to infinity. The x values, okay, going left to right, where the graph is going down is all of it, so negative infinity to infinity. You have a question? Okay. All right, so the next thing we're going to talk about are the formulas. They are on your pink sheet, and you get to use this pink sheet. Everybody pick one up. It's in the back. Okay. The reference sheet you will get to use on quizzes, tests, and the final. I have a blue copy, just like I had a blue copy of the other thing. So if you choose to write on it, it won't matter because I'm going to give you a different one for the test. Okay. The first box is exponential growth and decay. The second box is continuous exponential growth and the bottom continuous interest. Okay. The third is compound interest. You should have used all three of these last year. Did they look familiar? Okay. Compound interest, this is in your book if you need it, but the word annually means once a year, semi-annually twice a year, quarterly 4 times a year, monthly 12, daily 365, etc. Everybody okay with those words? Continuous interest, okay, which is not compounded daily, monthly, it's continuous, is this PERT formula. P stands for present value or principal, is what it really stands for. E to the power of the rate, which must be a decimal, times T, which is time in years. And that will give you A, which is the account balance or the future accrued value. All right, exponential growth or decay. Back when I taught this in Algebra 1, I wrote original equals 1 plus or minus some rate to the time. Does that look familiar? Yeah. What makes it plus versus minus? Yeah, is it increasing or decreasing, right? And then the rate has to be a decimal, so you got to, if it's 6%, you got to put 0.06 in there. All right, so example number 1. Do you have this question, guys? 2A. Biology. A researcher estimates that the initial population of a colony of cells is 100. So we're starting at 100. Original, or they will call it n sub 0, is 100. If the cells reproduce at a rate of 25% per week, what will happen in 6 weeks? Okay, T doesn't have to be years in this formula as long as it matches the rate at which it's growing. So if it's growing per week and we want in 6 weeks, then we're good. If it said per week and you want in 5 years, then you're going to have to, make it weeks so that the 2 units agree. All right. So we have 100, yes. For the interest formula, yes. All right, so this one is growing. How do we put this in here? 1 plus, oh, why did I put a plus? Reproducing would mean growing, right? And yes, 25%. And since this is per week, and we want to know in 6 weeks, as long as our units agree, we're good. So if you want to just type 1.25, okay. As long as it isn't asking anything future about this, you just do this on the home screen. Somebody get an answer? Okay. Yes. If it will either specify or I won't care. Okay. Number 2 says financial literacy. Lance has a bank account that allows him to invest $1,000 at 5% compounded continuously if he leaves it there for 10 years. So we do have years this time. The information that was important here was continuously compounded. So our present value, or his starting value, the principal and he put in the account, was 1,000. What goes in here? Instead of 1 plus 0.05, we're doing what? Continuous interest means E, okay, I really don't need the parenthesis, to the yep, okay, so P is 1,000, R is 0.05, and T is 10 years. So it's to the power of 0.05 times 10. which would be 0.5, yes. So 1,000 e to the 0.05 times 10. 1648, and this is money, so 72 cents? Yes. 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 And I will show you examples in just a second. But you're going to have to graph if you're trying to find the x, or the exponent, I should say. Okay. Compare the balance after 10 years of $5,000 invested, earning 8.5% continually compounded. Okay, so what are we going to use for that one? E to the, okay, which R is 0.085. Yeah, and then if we, T is going to be 10. Okay, someone can tell me what they get there. If you need it here, you mean, would be the only place? No, you don't. But if you have an older calculator, it will bring up a parenthesis when you type it like that. Does somebody have an older one that brings up the parenthesis? Anybody? Dakota? Yeah. So it would give you the parenthesis because it doesn't go up in that little box. Some of them don't. Anybody get an answer for me? Okay. Yeah, we went down to the penny when it's money because we want to know the difference. It says compare to the same investment compounded quarterly. Okay, whole new formula. P, anybody see where it is on the sheet? 1 plus R over N to the NT. Did I get it right? Okay. What is the P? 5,000. That's our present value. Parenthesis, 1 plus R divided by N. What's N? N is quarterly. So we're going to use what number? Quarterly is 4. So the interest of 0.085 is being divided out over 4 compoundings. And they're going to compound it 4 times a year for 10 years. So you can do to the power of 40 if you want. Do I need extra parentheses around this inside of here? The fraction? No, because it always divides, right? Calculator knows to divide before it adds. Okay. 5,000, 1 plus 0.085 divided by quarterly to the power of 4 times 10. 11,594.52. Anybody get that or not? Did I do something wrong? So what's the difference? Yep. What was this one? Somebody tell me this one again so I can put it on the slide. 11,52. And we said a difference of, now over 10 years, that doesn't, yes, that doesn't sound like much, but if someone offered me $103, I'd sure take it. Okay. if that was a question on a quiz, guys, I would give you blanks. Like if I want to know what this one came out, if I want to know what the difference was, I would make it specific because it just said compare there, which was kind of vague. All right, number 2, in 2007, it's estimated the United States used about this many quadrillion thermal units. I'm just going to go with that quadrillion as a label, okay? If U.S. energy consumption increases at a rate of 0.5% annually, what amount will they use in 2020? So which formula are we using? Does it say? Yeah, I annually means we're going to use this one though. So our original is 101,000. Remember, we have a label on that later. 1 plus 0.05. I'm wrong. What should it be, guys? It's 0.5. If we move it back twice, it's, yep. And from what? Our T would be 2020 minus 2007 or 13. 101,000 times 1 plus 0.005 or just 1.005 all to the 13th power. Did someone get this? 107.766 roughly. 107.766. It was comma, right? Not point. And that's quadrillion thermal, pretend I can spell, units. So annually was just once a year. That's why we didn't do continuous. Number 3, the number of rabbits in a field showed an increase of 10% each month over the last year. If there were 10 rabbits at this time last year, how many rabbits are there now? So what do we have to be careful of? Yes, so each month and last year. So we're going to do growing or increasing or decreasing. 1 plus what? 0.10, yep, or just 1.1. But this is a monthly rate, so if we want to hit 1 year, we want to do what? 12 months later, so yes. Compound interest is literally only for compound interest. Sure. Yep. Yep. A whole number's fine here. What did you get? 31. Okay. Okay. The population of a town is, I want to do this one because it says declining at a rate of 6% if the current population is this. Predict the population in 5 years and 10 years using each model. Do you have this problem or not? Okay. So we have 4 problems to do, I think, don't we? So we're going to do 12,000. No, I mean literally on this one. This is the original. Annually would mean it's going to only do the 6% once a year. So it's 1 plus 0.06 once a year for 5 years or 10 years, right? I don't know why they had to ask. And then we're supposed to do it continuously. So that would be using what? E to the 0.06 for 5 years or 10 years. All right, who's got an answer for me? Anybody? Yes, what'd I do? Oh, this is all wrong. Okay, you are so smart. I circled declining and then I ignored it completely. So this should be minus. Yes. This would be if I did the actual subtraction, and you can do it 1 minus. But if I did it, it's actually 94% are remaining. Everybody good with that? 6% of the people are leaving, 94% are remaining. I just wrote it 2 different ways to show you that you could use either one. Does anybody know what happens over here? What does it say on your little pink sheet? I think it says. No, because I already did that. 1 minus 0.06 is 0.94. I just did the math to show you could be doing it either way. But anybody know what happens? Doesn't it say on the pink sheet what to do if it's declining? Look, what? It does. Oh, you don't have that? You got to know this. Okay. Okay. You got to know this, guys. If it's decaying, you make a negative K. All right? Yeah, I must have said you had to know that. We'll practice it, so you will, but that makes the rate negative. So it's going to be negative 0.06 and negative 0.06 here. Can I just assume you guys could type those in and move on? Okay. Do you want me to give you a minute to do it? Will the difference increase or decrease between 5 years here and 10 years here? That they're going to be further apart, yes. The longer it's continuously doing anything, the further apart it will get from not continuously. Check your neighbor, make sure they're getting the same answers. All right, I have one more problem I want to do with you, and this one requires that we graph. You have this one, yes? Okay. It says use the data in the table and assume the population of Miami-Dade County is growing exponentially. So what is the original population? Okay. This is going to be our original population. Okay. Identify the rate of growth. How can we figure out how fast it grew? Okay. So 1.94 was multiplied by 1 plus some rate. How many times? 10 years. And became what new population? Okay. All right, guys, we're geniuses. We can do this. How are we going to work this backwards? Yes. 1 plus, oh my goodness. 1 plus r to the 10 equals 2.25 over 1.94. And I don't even care what it is yet. How do we get rid of to the 10th power? 10th root. Is there a better way to do that? To the 1/10th power. Perfect. And that'll leave us 1 plus r. So parenthesis 2.25 divided by what, guys? 1.94, close parenthesis, to the 1/10. We are for the second part. To the 1/10, or 0.1 up there, if you want to do that. I got 1.049. Anybody else get that? So what's the growth rate? If we subtract the 1, R is about almost 5%, 4.9%. Identify the rate of growth. What? Oh, there's a 1 here? Okay, thank you. So it's about 1.5%. Okay, 0.0149, if we moved it back twice, would be approximately 1.5%. All right, use your model to predict in which year will surpass 2.7 million. Okay, so we're going to put in our graphing calculator. Everybody ready to try this? Okay, 1.94 times 1 plus 0.0149. Yeah, I would actually like to do more places than that, but we're going to leave it. To the power of x. And then in y sub 2, what do we want it to hit? 2.7. Yes. From the question, it says part B, I want to know when it hits 2.7. So I go to my window. I can't have negative, and it's going to take it a while to get there. So I'm going to put 50 years in here, 0 to 50. How high? I really don't care about negative. I want to hit 2.7, so I really could say 0 to 5. Okay, now I want to find the point of intersection. So it's 22.3 years added to what? To 1990. So what year would that be? Sometime during 2012. Now, don't leave. I have a gift for you. This is what you're supposed to be working on, but if you want a copy of this chapter's bookwork, a hard copy, I printed it. You can write right on it like a worksheet. It's up here in the front. If that will get some of you to actually do the bookwork, take a copy. You don't want to kill a tree? Right in front of the blue baskets, that packet.